Good morning, class. Today is September 27th, and this is the video for the lecture on September 29th. And we're going to first go over homework 3, and then do a review for the quiz, which is Thursday. And the review will extend a little bit into nuclear power because that fits in with everything else. So let's just proceed here. So homework 3. So the first problem, this is a real thing. It's a real way to estimate the efficiency of an internal combustion engine, which you're going to see later is something that we need to understand to know how we can what electricity is going to be required as we use electric vehicles. And so this is, sort of, I'll call it a home generator. And put that in parentheses because, if, some of you may, have seen these things. I have one at home. You basically, and I'll try to sort of draw it to schematic there's a fuel tank up here, but basically there is a internal combustion engine. ICE, the acronym, and it's a fancy name for, in most of these devices, a lawnmower engine. Pretty much the same kind of engine you would see on a lawnmower. And while you can't necessarily see it, there's basically a drive shaft coming out of this thing that the engine causes to turn. So, you pull start this thing, and just like in your lawnmower, the engine will cause the blades to turn. Here it causes the shaft to turn, and that goes into the actual generator here. And, kind of schematically, wires come out of it. I guess I can sort of draw it properly here. On the side of this thing, there's an outlet. Okay, and you can plug things into it. And so this is a handy thing to have if the power goes out or anything like that. It's roughly shaped like a box, and the whole thing is called a generator, even though this is the engine, so to speak, and this is the electrical generator. And so, technically speaking, this is the generator, and it's being run by or driven by the engine inside the whole thing, which we're calling a generator. And now, basically, the problem was to calculate the efficiency of this internal combustion engine, and to do that, I said you could assume that the efficiency of the generator was 90%. I think. Yes. Okay, and we'll learn later why the efficiency of electrical devices that convert either work to electricity or back again is so high, around 90%. And so the idea here is that the total efficiency of the unit is the products of the efficiency of the internal combustion engine and the efficiency of the generator. So the efficiency of the internal combustion engine is equal to the total efficiency divided by that of the generator, or the total efficiency over 0.9. And the total efficiency comes from, and this is why I wanted you have a fuel rate going into it, and that's able to provide an electrical power coming out. And so the total efficiency is the fuel power, and this is why I wanted you to get used to the idea from the other problems of thinking of a flow of fuel as equivalent to having a power. And I wrote this backwards. That's on the denominator. And so you divide the output electrically by the fuel power input. And what I told you is that the output is 5,000 watts, and that's so it consumes 1 gallon per hour. Okay, and here our units come into play. So that's equivalent to 124,000 BTU, all right, per 3,600 seconds. Okay, and you multiply that times 1,055 joules per BTU. And so if you work out those numbers, it works out to 35,960 watts. So this is your electrical output divided by the fuel input, and so when you plug that all into there, you get that the internal combustion engine is equal to 0.154, 15.4%. So this is sort of the first approximation we can do to what we'll be trying to do later, which is determine for a average vehicle, whether it's a car or a truck or something like that, what the equivalent efficiency of that vehicle is. And of course it depends on how it's driven and what conditions and what speed and things like that. But this gives you your first impression, at least, that the efficiency of an internal combustion engine is far lower than an electric motor. Now, we're going to see later that part of this is inherent due to thermodynamics. Part of it is due to unavoidable losses, friction, things like that. And what we're going to see roughly is that for your modern car, at least within the last few years, that through a variety of techniques, the modern car engine has brought this number up from around 15% for this little lawnmower engine to around 25%, and maybe in the future 30%. So that's where we're going with this. So the problem had two purposes. One was to get you used to the idea of thinking about problems like this, and the other was to start thinking about what this actually is. Okay, so problem 2. Okay, so problem 2 is kind of fun. And basically, the thing here is that what you've learned is that when you have, a well going down here, and it doesn't, I mean, basically oil can flow in here. And what you've learned, and this sort of starts our review of that section a little bit, so allows us to save a little time there today. That what you've learned about both oil and gas wells, well, particularly oil wells, is that when you first plunk this hole down in a conventional vertical well, that oil is under so much pressure down there that it comes blasting out, and so you don't have to do anything. You just have to cap it off and control that flow so that you can load up tankers and barrels and whatever you want to store it in and sell it in. And what happens is that, and we can use this as our review for oil. What happens is that over time, that pressure gets lower and lower. All right, and okay, what can you do? Well, you can drill a well off to the side here, and you can put down water. And that water pressurizes the well, and so it comes flowing out again. All right, now, when you do that, for example, you can, you know, this is like in Saudi Arabia. All right, when you do that, what happens is that you get oil plus water there, and so over time, in order to keep that oil flowing, you got to put down more and more water, and so the amount of water in this fraction here sort of is a good determination of how much oil you got left down there, because you're basically using it to push the oil up. All right, so you know, problem 2 didn't have anything to do with that, but what happens sometimes is, okay, either because there's no practical way to pressurize the well, or because you have pressurized the oil reservoir, but you just simply can't do it anymore, you have to basically lift the oil out. Lift. And so you have this pump jack, and I can't draw it properly. It's basically a thing that goes up and down, and there's some linkage there, and it, you know, there's a drawing of it in the homework that I'm not going to put the screen up here, but it's kind of a clever mechanism, because basically it fits in there like a piston and a cylinder kind of, so that when this thing goes down, okay, it opens up and lets oil in above it, and then when it goes up, it pushes that oil up. It closes its opening and lifts it up, and so it's doing this, and it's you know, it's basically lifting up this column of oil continuously, and so you get a little bit of oil, you know, flowing out here. It's not under any pressure. It's just, you know, at atmospheric pressure, and then you can load barrels and stuff like that. And you get the idea that once you're at this point, okay, your production rate is really low. Remember, well, we didn't really discuss what a particular oil well did, but, you know, I mean, you might get, you know, 1,000 barrels a day from a conventional oil well when you first dig it out, because of the pressure blasting this stuff up. You know, doing this, you might get, you know, a few barrels per day. All right, and so, you know, you're not going to get rich off of these things. You know, barrel of oil costs, you know, these days, I don't know, $50, and so, you know, each one of these, you know, is you know, giving you $150 every day, and so if you have a whole bunch of them, you're making some money. But anyway, the problem was to determine, okay, this lifting energy, okay, is it worth it? Okay, now I told you to assume that the efficiency of the pump here was 100%, which is not true. But, you know, this gives you an idea of things. So basically, the energy returned on the energy invested is equal to the energy content of the oil, because I'm saying 100% efficiency. And so that's 38,700 That's, you can look that up in the notes. That's for the average for crude oil, BTU per kilogram. All right, times 1 kilogram over GH, where this is 9.8 meters squared per second squared. And for that, I told you to use 7,000 meters. So you take 38,700 divided by 9.8. Oh, and you got to multiply times 1,055 to get it in joules. So that's the ratio of the joules in the oil divided by, if you multiply that numbers, it's 595. So basically, if you consider that the pump has 100% efficiency, that the energy required to run it is simply the lifting energy to lift out of the bottom of the well. 7,000 meters, is a good far down. That ratio is 595. So on an energetic basis, yes, it's very much worth it to do this. You don't make money very fast, but you can use this as kind of a guide to form a business model that, okay, say I buy one of these, I want to know the operating cost versus the amount of money I make. I mean, you would calculate, how much electricity you're going to consume to run that pump motor, and you would determine that, yeah, your operating costs are actually a pretty low fraction compared to what you make. Okay, so that was problem 2, and I'll just erase that and go on to problem 3. So problem 3 was to talk about compressed natural gas vehicles. And so, this was a simple exercise. And so I'm saying you have a car. Horrible drawing cars. All right, you have a car here, and in here there's a tank. And now, when I was making up the problem, I was trying to look up, okay, how big are these tanks? And I couldn't really, find it, because they didn't sell the tanks in, what their actual volume was. They kind of sold them in what energy they could contain. Okay, so they were essentially specifying the size of the tank based upon actually having already solved this problem. But I used 12 gallons actual volume. Compared to standard, so to speak, put in quotes, 15 gallons for a gasoline car. And the reason why was I figured, well, okay, in principle, this tank, it has to hold this compressed gas, and so it's going to be thicker and everything, and I don't know. I just made it up. Okay, so 12 gallons actual volume. All right, and so it's a simple problem now, because 12 gallons, so that's equal to 1.604 cubic meters, or cubic feet. And you just do that conversion, and atmospheric pressure is 14.7 psi, pounds per square inch. And so the way to think about this is that V at atmosphere over V of the tank is equal to P of the tank over P atmosphere. Or the pressure of the tank, I said, was 3,000 psi. P atmosphere is 14.7. And so, I mean, at least this is the way I thought of the problem. There might be other ways to think about this problem, but basically, I wanted to get V atmosphere. So V at atmospheric pressure is equal to 3,000 over 14.7 times 1.604. So the point is that the original volume before you compressed it of the natural gas, 3,000 over 14.7 times the size of the tank. And that gives you 327 cubic feet. So when you filled the tank, now I mean this is again kind of, you know, we're you know, thinking in terms of everything being 100% efficient and stuff like that. The compressor compressing the natural gas may have some losses, I don't know, things like that. But this is an ideal problem, and it's saying that when you filled that tank at 3,000 psi, you started with 327 cubic feet of natural gas. And you know, I mean, I use 1,000. I mean, you can use BTU per cubic feet. That's a rough number, 1,000. And so it contained 327,000 BTU. Now, off to the side here, my gasoline with the 15-gallon tank is 15 times 124,000. It's equal to 1.860 BTU. So the range, the fractional range, is 327 over 1860, 18%. Which I thought was kind of interesting, that, you know, this calculation indicates that you can only go 18% of the distances you could with your standard gas car. Now, I don't think that's actually the case. I think most of these vehicles can go a lot further. For example, Honda used to sell a natural gas vehicle that was rated for, I thought, 200 miles.